screen. Okay. Hello everyone. So welcome back to the numerical simulations in metal forming course. And today we will be talking about simulations of sheet metal forming processes. So in the past we have done the we have studied about rolling processes, forging processes, and now we will focus on the sheet metal forming processes, which are intrinsically different from the other bulk deformation processes but are very, very important. And in this lecture, we will go through why that is the case. Before I start my lecture, I want to tell you that you can write me a private question or write a question in the public chat, and I will be able to see it and I will respond to it at appropriate places within the lecture. It will be great if you can interact as much as possible so that you do not miss anything, and yeah, we make it more interesting and more interactive. So yeah, Professor Ulrich Prahl is basically responsible for this lecture and for this course, and me and Mesam are delivering the lectures. Um, now we are at this position, you would know. And I want to mention here a few things. Because I was sick in the last few weeks, so I was not able to deliver this lecture here. And we have one more week to go, so that will be this topic here. But then this topic will be missing, which is artificial neural networks and simulations. So these two, multi-scale modeling and crystal plasticity and artificial neural networks and simulations, are very futuristic topics, I would say. These are the state of the art on which the numerical simulation models are currently being built on. And they basically give an outlook into what is happening recently in the numerical simulations field and what the researchers will be focusing on more in the future. So these are the topics which I really want to cover, and the multi-scale modeling and crystal plasticity is also part of my doctoral thesis work. So I am very excited to deliver that, but we only have 1 week to go. There are two possibilities. One is that I will set up lectures in the next week at two different dates. Whoever will be able to join me can join me. I will deliver the lectures, record them, and upload them on the portal. And the other possibility is that I do not do live lectures. I only record the videos um, and then upload them on the portal, and everybody can watch the videos. And if you have any questions, you can put them in the comment section there, and then I can answer them there. But they are important, and we will somehow try to make it possible that you have that information before you prepare for the examination. Yeah, that's the information which I wanted to deliver. And now let's look at the objectives of today's lecture. So in today's lecture, we would want to understand what is sheet metal and why its forming is so important. Um, we will also want to understand the attributes and properties of sheet metal and how they are slightly different from the bulk materials. We will learn simple calculations for different sheet metal forming operations. Then we will use and apply the simple calculations for solving simple related problems. And to clarify the concepts I have sorted out some videos which we will be able to watch together, and then we will discuss them to see what we learned and how the different processes are can be helpful. So um, we will start with we are talking about sheet metal forming. Um, so that is a very specific technical term. Do you know what is the difference between a foil, sheet, and a plate? Um, and I will start a poll for that. Do you know what is the difference between a foil, sheet, and a plate? No. Okay. Yes. And if you know, what I would want you to do is put the answer in the public chat so everybody can look at that. And then I will, of course, share it here. If you don't know it, a quick Google search would be very helpful, and then you can list your answer in the public chat. So we have 1 or 2 minutes for this activity, which is interesting. Um, but if you don't know the difference, I want you to make a quick Google search and yeah, find out what that is. Okay, so almost 70% of the students didn't know the difference, and yeah, the answer is correct. So the difference is the thickness. What are those thicknesses? That's the question. Okay. Um, so the sheet metal with the thickness of less than 0.2 millimeter is considered as foil. Sheet metal with a thickness of more than 2 millimeters and less than 6 millimeters is considered sheet. So that is the tolerance. So this is the tolerance which we will be talking about today. We will be discussing it in most of the cases. And blocks with a thickness of more than 6 millimeter are considered as a plate. I hope that is clear now. So so today when we talk about sheet metal forming, when we talk about sheet metal forming, we will be talking about these um, limits of between zero point 0.2 and 6 millimeter. Depending on the book, depending on the blog, these dimensions are slightly different. The 6 millimeter is quite conclusive, where all researchers agree, but the 0.2 millimeter, is slightly can slightly vary. Um, and then I have another question. What is the difference between a tube and a pipe? And you can write your answers in the public chat, or I would just quickly start a poll to see if you know a difference between tube and a pipe. And if you don't, a quick Google search would be very appropriate. And if you know the answer, can you also share it in the public chat? Um, so these are very basic and simple questions of what is the difference between a foil sheet and plate, and what's the difference between tube and pipe. And I am encouraging you to and I intentionally um, tube can be rectangular but pipe is always round is partially correct. So one of the differences is that, but there are many others. Um, I will publish this poll and move on. But if you want to know about it, there is a very nice link with all the details about the differences, all the differences in the pipe and tube. But you can also search it anywhere you want. And I intentionally had put these questions at the beginning because um, in your study period or after you finish this course, you will come across many questions which you will not know the answer to, but will be important to solve a problem or to go further. And then you should have a habit of finding the answers online and trying to do a simple quick Google search to find out all the answers. Okay, so now once we have defined what a sheet is, which is basically um, a thin piece of material which has thickness between 0.2 millimeter and 6 millimeter. Um, this kind of material, so this kind of shape has specific attributes and properties attached to it. And one of the main properties and attributes which are attached to it is anisotropy. Um, so the students write pipe is a vessel while tube is a structure. Um, True. It depends on how you are defining vessel and a structure. Pipe is a hollow section with round cross section for the conveyance of products. The products includes fluid. Okay, yeah, yeah, they're all correct answers. But there are many things which distinguish a tube from a pipe, depending on the application, depending on the internal radii, depending on the thickness of the wall, and so on. Again, this is not the um, topic of current today's um, lecture, so that is why we are not really going deep into it. But it is important to know that, and you don't have to remember it when you can just do a quick Google search and find out all the answers. Um, Again, when we come towards sheets, um, I don't know. Oh, okay. Um, so what happens is that due to continuous rolling operation, we have discussed rolling, right? Already, and we know that rolling process is used to convert thick billets or slabs into the desired thin thicknesses. And we have already discussed this, that to reach a thickness of as low as 6 millimeters or even below that to 2 millimeters and 3 millimeters, hot rolling or warm rolling processes are not very adequate. And we do cold rolling to reach that level of thickness with the appropriate surface finish. And when we do that, what happens is that the microstructure of the roll sheets aligns in a certain direction. As you can see in this figure here, that this was the rolling direction, and the microstructure of the material is aligned in that direction, which is elongated in that direction, with all the second phase particles, which you can see here as black particles, are also all aligned on relatively singular lines. And what happens is, and this picture is taken along the thickness of the sheet. So basically the sheet is longer in these directions and very thin in these directions, but it is a very magnified image. So what happens is that when we will try to load this sheet in these directions, in this direction it will behave differently than when we will try to load this sheet in the other direction, because the microstructure is more aligned in that direction, the second phase particles more aligned in this direction. What will happen is that um, it will have relatively more strength in that direction and will show more ductility in this direction. And in the transverse direction, we call the other direction the transverse direction, it will fail quite easily and will deform less because the microstructure is not neutral. And this difference of properties in when loaded in one direction then when loaded in the other direction is called anisotropy. And this is one of the intrinsic attributes of sheet metal because of its manufacturing process. So there are two ways of going around it. One way is to know what is the anisotropy in the sheet material, and the other way is to do annealing heat treatment, where we heat up the sheet above the recrystallization temperature of the specific material and then let it cool down normally. And then what happens is that these grains all dissolve together and then recrystallize, and then this aligned microstructure is not there anymore. Um, so the disadvantage of that will be that the sheet will then be normalized and will have a neutral microstructure, and it will not be strain hardened. So it will not have very high strength. So that is another attribute which we will lose after normalizing. So it is always complicated to choose the 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 sheet and understand its anisotropy or do normalization and so on and so on. But just know that the sheet metal will have this intrinsic anisotropy attached to it. So we either have to know it or we have to resolve this issue by normalization. And then the other thing which the sheet materials have is they basically are singular plane um, systems, which means that when there is very less thickness, we can assume that there will not be any stress in the third dimension in the z direction, and all the stresses are basically present in the x and y direction as shown here in this picture as shown here in this picture. So when we will apply load in x direction, we assume that the material will only decrease in the y direction. So that if there are positive stresses in that direction, there are only negative stresses in the y direction, and because its thickness is too low, there will not be any stresses in the z direction, and we call this a plane stress condition. And also for the case of shear stresses, all the shear will only be present in the x and y axis and not in the other axis. This assumption helps to convert a 3D problem, which actually is, into a 2D problem, which can then become much easier to solve analytically if we want to do that. And also, this is an assumption which we take in the numerical simulation models, where we take a sheet and along its thickness we consider it as a plane stress sheet, so the computer does not have to solve all the equations in the third dimension but only two dimensions. So that makes the equations very short, very simple, relatively easier and faster to solve, and yet the results are not much different. Of course, this is an assumption which makes the results slightly different, but depending on the case, the results are not highly different, and we can get the desired results quite quickly. So that is also something which is attributed to sheets, that uh, generally that the plane stress condition exists in them. Um, and after the assumptions, let's come to a point on why is sheet metal forming so important. Um, and when we want to discuss this, it is important to understand that our lives are surrounded by sheet metal components. Um, for example, automotive body parts, aircraft frames, major home appliances. Can you think of some appliances which are completely made of sheet metal? Or are majorly made of sheet metal? Can you think of some appliances in the home? For example, let me give you an example. The body and overall structure of a washing machine is made out of sheet metal. So the outer cover is all sheet metal, and then it is bent into the desired shape. The inside drum is also sheet metal which has been bent to make round, then it is perforated, and then it is welded together to form, and then they are directly assembled together with the help of a motor and all the electronics and so on. So the sheet metal is a basic process or a material which is used to construct this appliance. Can you think of any other appliances? And that's a question which automatically expects an answer. Anything. Can you think of something in the kitchens? Or can you think of something in the basements? Or can you think of something in the um, bedrooms or the living rooms? Fridge. Yes, that's a really nice example. Cupboards or um, yeah, some parts. Microwave oven. Yes. So majorly made of microwave oven is a really nice example because it has two frames, an internal one which is made of sheet metal, and then an external one which is also made of sheet metal, and then a base which is made of sheet metal, and everything is held together with the help of spot welds. And yeah, building fixtures, for example, corrugated rooftops, wash basin. Yes, that wash basin is also a really nice example of sheet metal parts. Yes. So you see that a lot in many parts of our lives, sheet metal parts are very common, and they play a huge role in defining the lives around us. And then again, let's continue with um, um, building fixtures and structures. So there are many components in building fixtures which are used of sheet metal. Some of the, if we go towards technology, some of the antennas where large area sheets products are used, specifically radio antennas. Um, and there are countless applications for smaller sheet metal parts in our lives. For example, washers, beer cans, kitchenware, and utensils. So utensils, all the um, are also majorly made from sheet metal. We have a flat plate and then we deep draw it. That is what we will study today. And there is a nice example given on this slide, which is a whole car body part. Car body is made from sheet metal formed parts, and which are later joined by welding. And that is a very interesting example for which I have a quick video about, which I would like to share with you. Um, no, what I want to do is I want to put it here. I want to make it big. Uh, yes, and then I would turn on the music. So this is an example of how the car body parts are generally manufactured. So you see here that all the um, sheet metal rolls are coming into the industry. Here they are being unwound. The roll is being opened and then fed into the cutting press, which basically what does is does blanking. The process is called blanking, where um, sheet metal parts are cut out of the whole big um, product, and now they're being stored in the store for the later use. And here you will see the press shop. These are the dies which are used to um, do the sheet metal bending and drawing and all those steps which are needed to convert these flat sheets into the desired shape. So these now those cut parts are being fed to the press. Um, and what is happening here is that the dies are being sent into the press. So now you will also know the trends of industry 4.0 and automation, where the dies are automatically going in depending on which parts do we want to manufacture, and then those flat parts are being fed into different dies, are being formed at different steps, and then you see here that the formed parts, the sheet metal formed parts are coming out. So this complex forming is not done in one step, it is done in multiple steps. It is a combination of sheet drawing, sheet bending, shearing, forming, and in the end we get these kind of complex shape parts. The example is for a car, and then these parts are being stored in the store again for the later use. Depending on which model they want to manufacture, depending on um, how and when and where the model is being manufactured, different parts are then extracted from the stores and then shipped to the site where they are then used. But here, this video will end here, where they are basically doing an automatic inspection of the part with 3D scanner, and which shows the how the tolerances of the shaped part do compared with the actual geometry which they gave in. Okay, no, we don't want to do that. No, we don't want to do that. Okay. Okay. So yeah. Um, so so you see the structure here, which we will see, which we will watch another video about. Basically, is a combination of a lot of sheet metal forming steps, and then these individual components are made, then they're joined together, and then we see this whole structure. Um, so that is why the sheet metal forming is quite important in our lives. Um, and that is what we want to study today. Um, the sheet metal forming operations can be generally classified into the following categories. Based on the outcomes of the sheet metal working, they can be classified into these processes, where one of them is shearing, one of them is bending, and one of them is deep drawing. We will study them one by one. We will see what they are and how they perform. And on the other end, we also have operations performed without presses. And these operations are basically stretch forming, roll bending, spinning, and tube bending. And that is also something which we will study today. Probably not tube bending, but other than that, all the others. Um, so yeah, as we saw earlier, several simple sheet forming operations join to form complex shapes. These form parts are then joined together to manufacture desired components. These assemblies serve as the skeletal structure of equipments and machines. And the few links are here, which you can later watch for your understanding and convenience. What I will do here is I will quickly try to find one case of, yeah. So what I will do is I will quickly try to just share one interesting case with you. Can we? Yeah. Okay. So the audio is paused. Let me start that and make it lower. Okay. So in the previous video, you saw how the the rolled sheet metal comes into the factory, how it is blanked into the desired um, blocks, which are then used to form and make into the desired shapes. Now this is basically the next step which comes in car manufacturing. So all those blocks are then come down from the store into the assembly plant, where here you will see the robotic arms actually picking them up from the conveyor belt, putting them in the jigs and fixtures at the right points, and then welding them together to form components, which will then later be used in the cars. Um, we want, okay, so here, there is a big skip here, but generally you see that how those components individually built together one by one, welded together, can form this kind of basic car frame. um, and here you will see a lot of operations being going on, where when the parts are initially joined together with a few spots, are then later welded together more appropriately, more um, strongly, using spot welds. Um and yeah, so this is the basic car frame, and the process goes on where it slowly takes the shape of a car. Um, Spot welds are still going on, and yeah, and if you look at this structure, it is mostly made of. I would say more than 95% of the components. A few are just um, the bars, but most of them are sheet metal parts which are joined together using spot welds. And then the video will go on to include more larger components to this block, and it will directly take the shape of a car. I'm just waiting for that to happen. Yeah. So now the adhesive is being applied to the parts which need to be added to that frame. And after the adhesive has been applied, you will see it is just one single big side block which will be added to the car. Yeah. So you will see here that these are really two big components made out of single piece of sheet and then assembled together on the side frame. And then the roof comes in, and then you will see other components added to the car, and probably by hand, yes. So all the fixed components were already installed to the car, and now the movable components are being attached here. But the important point, which is important to see here, is all these parts are made out of sheet metal. So, the point of showing you this video is to put things in the perspective that um, how the simple processes or methods which we will study today can be helpful in making these kind of machines and components, and why they are so important. Because all the parts and components you're seeing here are made from processing of sheet metal. So yeah. Um, so what you can do is go and watch the other videos for understanding the bigger picture as well. So now let's come towards the individual steps which we discussed. And one of the main steps is shearing, which is cutting of sheet metal um, accomplished by shearing action between two sharp cutting edges. And um, in this process, um, as you can see, it goes from 1 to 4. Um, uh, we have a die, this one, and we have a punch, this one, and um, the sheet which we want to shear or basically cut is then put between the die and the punch, and the punch begins to push into the work. The plastic deformation takes place, as you can see here, um, occurs in the surface of the sheet. As the punch moves downwards, this plastic deformation um, reaches its limit, and it reaches a point where um, uh, penetration occurs in which the punch compresses the sheet and cuts into the metal. Um, this penetration and then shearing basically results in the fracture. Um, the penetration zone, this one, is generally um, 1/3 of the thickness of the sheet. As the punch continues to travel into the work, fracture initiates in the work and the between the two cutting edges, and shearing takes place. And this is how we cut sheets in a simple way. Now, when we cut a sheet, it has different artifacts. So you will see that um, the surfaces are not very straight here and here and here and here. So as the shearing takes place between the two edges, there is a slight um, uh, deformation lip here, and then there is bar. We call it bar here, and and they are important. We don't want these plastic deformations to be too large, and we don't want them to be too small. We want to keep our tolerances. So if we want to cut a very small piece of 3 millimeters or 4 millimeters, we want to make sure that it is 3 millimeters and 4 millimeters, and therefore we want to make sure that the part is of desired size. We need to maintain this clearance. Hmm? And there are some basic calculations for doing this kind of analysis, and a basic formula to calculate clearances is this one, which is shown here, where clearance is a multiple of clearance factor and the thickness of the sheet. And this clearance factor, AC, depends on the material hardness. So um, the softer the material, the lower the value of AC. You can see here. Um, these values have been empirically calculated by doing a lot of tests, by doing a lot of and then corresponding calculations. The researchers and scientists have found out these values empirically. So they do not have any um, derivation or why they are like this. They are just fixed constants. Um, so you will see here that and then in the soft, medium, and very hard materials, there is a difference. There is a complete list you can read in the given textbooks and so on about this clearance factor. But yeah, the multiple of this will give us the clearance. And then there are different and then there is a force calculation, which basically is the which in simple terms is basically the shear strength of the material multiplied by the total length of the shear area. Because we know that the shear strength of the material is almost uh, 2/3 or 70% of the tensile strength of the material. Therefore, we can change this S, the shear strength of the material, to this, and this L remains fixed. And if so, this we will use this formula if the plate which we or the sheet which we want to shear is flat. From if I show it from the top, we have this kind of plate which we want to cut from here. And we can use this formula if the material which we want to cut is basically circular. Out of this sheet we want to cut this, then we can also use this formula where the total length is basically the circumference of the circle. Um, um, Now in these equations, the value of force will be quite high, and that is because in these formulas we assume that the entire cut along the shear edge length is made at the same time. So we assume that a punch goes in and cuts the whole blank simultaneously. In this case, the cutting force will of course be maximum. It is possible to reduce the maximum force by using an angled cutting edge. on the punch and die, and I want to show it to you, but no. Um, let's see where I can show that. We can start a whiteboard and clear canvas. Okay, so for example, um, if we look it from, let's take an example of a sheet which I want to cut from here. So if I will put it between the die and the punch from this side, it will look like this is the sheet, a little longer, and this is my die, this is my punch. And from the front, if I will look it from here, so this is the side view and this is the front view. Uh, the sheet is here. This is the die, and my punch is like this. So when I will press it, it will simultaneously be in contact with this whole length, and it will cut it. But and then of course this will have maximum. This will result in maximum force. And what we do instead is we use this kind of punch. So what it does is it comes in. So when we press it, oh, so when we press it, it comes in contact with only this section of the sheet, and then when this is cut, it comes in contact with this section of the sheet and this section of the sheet, and and that is how we reduce the amount of force needed for the shear. And similarly, we can also do it for a circle and so on. uh, I hope it was understandable with this kind of schematics. So yeah, so this force calculation is basically for the total complete cut. Of course, it can be for significantly reduced if we do incremental cuts. Like in the case of scissors, when we cut something with the scissor, we require very less force because we are only cutting a very small area, and then we incrementally do that. The total amount of energy required will still be the same, but the amount of force required at one moment will be smaller. And then there is this next sheet metal forming operation, um, which is called bending. And bending operations are performed using punch and die tooling. The two common bending methods are associated with and associated tooling are V bending performed with the V die, as you can see in V bending, which you can see here, and the other is called edge bending, which you can see here, are performed with a whipping die. In the V bending operation, it depends. So the die is fixed with a certain angle, which you can see here, alpha, and we use a punch which has a same angle inscribed, alpha, and then we push the sheet in this angle, and then we get with an adequate force, and then we get a bent sheet. Um, so for this process, uh, the angles can range from very obtuse to very acute angles. So it can be from very close to 180 degrees angle, uh, where we just make a small bend, to very acute angles where we make a very sharp bend, or um, make the sheet in quite around. And then basically this radius can also be incorporated in the sheet if there is a radius given in the punch and the die. And on the other hand, we have edge bending that involves cantilever loading of the sheet metal, which is shown here. A pressure pad is used. This is a pressure pad which is used to apply a force and hold the sheet in one place, and then a punch is then used to bend the die. Um, Now, in in both these cases, there is a difference in both the angles, and for example, in this case, there is a gap between the die and the punch, and this is called clearance. And we need to cater for this depending on how what is our angle of bending and so on, and we call that bending allowance. And it is important um, to understand that if the bending radius is small relative to the stock thickness, the metal tends to stretch during bending. Um, so, for example, if I want to bend a sheet, let's say, let's try to make it as close to reality as it would be, and I will put my punch very close, and then I would try to force it. What will happen is that this sheet will get thinner at this edge during bending, and that is what we don't want to that is what we don't want it to do, because it will reduce its strength. So what we want to do is we want to calculate this. We call it AB, bending allowance. We want to calculate it more accurately, so we can give this bending allowance between the die and the punch while bending our sheet, so it does not stretch and does not lose its strength. And the formula to do that is given here, which seems relatively complicated, but it is quite simple, where um, this is basically a calculation for the um, the the bending angle, um, and then this is basically the radius of um, the yeah the radius of the bend, which is mm, oh, which is, let's make it, so there are two things. Let's take an example of this. So one is this angle alpha, which is given here, and the other is this radius of bending. And then of course we have our thickness of the sheet, and then there is constant factor to estimate stretching. Now, generally the following design values are recommended. If the radius is less than 2 times thickness, this value of kb is used, and if the radius is greater than or equal to 2 times of the thickness, then we use this value. And from this formula we calculate the bending allowance. um, and then there is also an intrinsic um, attribute which is called spring back, um, associated with the sheet metal bending operation. Because what happens is that when we deform a material, there are two components associated with it. One is the elastic deformation and the other is the plastic deformation component. Plastic deformation one is the one which is the permanent deformation, and elastic deformation is the one which is elastically stored. And then just um, recoils when we remove the load. And in the case of bending, this is quite significant. So we want to calculate um, the spring back in our sheet metals. Now there are several many formulas that are related to um, the um, calculation of the spring back, but here we are just calculating spring back in terms of percentage. So what was the intended angle and what was the angle which was achieved during during deformation, during bending, and then we just calculate the percentage of spring back. So this was the spring back. What we can do is we to avoid spring back, or we cannot avoid spring back, to reduce the amount of spring back. What we do is we do an overbend and then we release load so it reaches our desired level of deformation. So for example, here there is in this diagram there is shown that um, a sheet has been bent, and when the load was applied, this is where it was, and then when the load was released after spring back, it reached this limit. Now, if we want to achieve this bending and we want to avoid this, what we will do is we will overbend it like this and then release the load. And after releasing load, it will reach at this position. So we will have our desired shape of the sheet, yet it will even after spring back. And that is why we want to calculate it and um, calculate the spring back, and um, that is why it is so important. Then we come towards sheet metal forming operations, for example, deep drawing. It is quite an interesting operation. It is used in many different ways to manufacture many different types of parts and components. Here we will only see a simple cup-shaped deep drawing process. Um, it is a basic a blank is drawn into a die cavity by means of a punch. So you can see here that there is a sheet between the blank holder and the die, and we just push the punch through, and the sheet is formed into the desired shape. The details of the process are given here, where, for example, we see that when the punch first begins to push the work, the material is subjected to a bending operation. So we see here that bending is taking place here and bending is taking place here. And then as the punch moves further down, in case of this figure, a straightening action occurs. So there is a bend first and then it becomes straight here. Um, that was previously bent over the die radius. So this causes the strain hardening effect in the material because we are bending it first and then straightening it later. And that makes the wall of the drawn part relatively stronger than the lip or the bottom of the part. And then what happens is that for the material in the flange to move towards the die opening, um, the, the material wants to flow in. There are two kinds of forces acting. One is a hoop stress here at the lip of the point, and the one is the tension which is pulling the material inwards. Um, the surface of the blank holder and the die, for the material in the flange to move towards the die opening, the friction between the sheet metal and the surface of the blank holder and the die must overcome. In addition to friction, compression is also occurring in the outer edge of the blank. So yeah, there is frictional force here which does not want the material flow inwards, but there is a tension force in the wall of the component which wants the material to flow into the die cavity and doesn't want to break up because it has been strain hardened. And then there is a hoop stress in the lip uh, or here it has been written in the outer edge of the blank when it is circular, which does not want the material to flow, but um, depending on the amount of force and the speed and so on, the material eventually flows into the die cavity. And then the progressive downward motion of the punch results in a continuation of the material flow caused by drawing and compression. In addition, some thinning of the cylinder wall takes place. So the cylinder wall gets slightly thinner because it is stretched. So there is a lot that happens in the in the drawing process, and seems simple, but there is a lot happening, and that is why and 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 it is a very important process which is used to make a lot of different types of components. So that is why it is quite important and interesting. Now, some basic calculations for sheet drawing operations include um, draw ratio. So we can calculate that easily by dividing the blank diameter with the punch diameter, and then we get a draw ratio. Now it is important to understand that the upper limit of the draw ratio. It is important to understand that the upper limit of the draw ratio is 2.0, which means that um, if the diameter of the blank is more than uh, two times the diameter of the punch, it will be quite hard to draw it inwards. It will cause earring on the outer edges. It will cause tearing in the wall because the um, tension in the wall will not be able to pull the material through the die. And there are many things that take place, but yeah, it is important to understand. And then we also want to do force calculations, where um, force is basically um, a combination of this formula, where T is the thickness of thickness of the sheet. This is the punch diameter, and then the tensile strength of the material is incorporated in here, and then of course we have draw ratio here minus 0.7, and we do all these calculations. Uh, um, and then this 0.7 is basically a correction factor to account for friction. Holding force, which, if let me go on the previous slide, which is being applied here to hold this blank down, is also important. Um is an important factor in drawing operation. And a rough approximation is that the holding pressure can be set at value of 0.015% of yield strength of the sheet metal. And that is because we want to hold the material flat, but yet we want it to flow into the die cavity and not be held there, and the tearing takes place in the wall. That is something quite interesting and important, and we will study this in during the next lecture when we will talk about the case study of drawing process. So now what I have done is I have shared. Let me bring it here. So what I have done is I have shared an Excel sheet in the, if you will go in the numerical simulations in metal forming course, and you will go in the learning material, and you will go in extra study material, you will find this sheet forming calculations Excel sheet. And if you can download that, it will be very interesting to use these formulas and run some basic calculations. Um, Once you have downloaded that, please inform me about it so I can start a poll. So I want to ask, have you downloaded the file? super, and the file will look something like this. Okay. Okay, there is no point in doing it, but I will still do it. Okay. Hmm. 200. Hmm. So this is just a very small calculator which I made. So if you have voted no or you have not voted anything, I would like you to ask to please cooperate and download this file because it is an interesting activity which we want to do together and see the results for. Okay, so what I would want to do here is um, you see here that this Excel file contains three different sheets. So below here, if you will take a look, there are three different sheets. One is sharing, the second one is bending, and the third one is drawing. So the formulas which we saw on the slides, what I have done is I have incorporated them in this. So what I've done is I have incorporated them here in this list, in these individual sheets, and you can play around with them. So for example, if you want to do some shearing calculations, you can write the thickness of the sheet, which can be, for example, let's say 4 millimeters, and the value of the clearance constant. Do you remember we studied about it? So if the material is very soft, the value is 0.045. It is a drop-down menu, and if it is medium hard, the value is 0.06, and if it is very hard, the value is 0.075. Let's assume that the material is super hard and the value is 0.075. Then the clearance for the edge should be 0.3 millimeter for a 4 millimeters sheet. And if it is 0.6, then the clearance can be less, and for 4.5 the clearance can be super low. Okay, and then what we want to do is we want to do force calculations for a circular disc. So I'm doing the force calculations for a circular disc, but you can also make a similar sheet for the straight cuts. Um, so I say here that the radius of the disc is, hmm, let's say 7 mm, and the sheet thickness is, let's say, 2 mm. And the tensile strength of the material, it then depends on the material, and you would know that from the testing of the material. That is also something which we've discussed before. But let's say it is a very soft material and the tensile strength is 250 MPa, then the force required to shear the sheet in all together at once is 15 kilonewtons. Hmm? Now let's do another um, 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 case study. What I want you to do is um, I want you to uh, I want you to do a calculation for um, a round sheet which is 10 millimeters radius, and then the thickness is 5 millimeters, and the ultimate tensile strength is 400 MPa. I want you to find the force required as well as the clearance needed for this case. And you can just quickly do these calculations using the sheet, and just write your answers in the comment section here, and then we can move forward with the further calculations. Clearance is 0.3 and the force required is 87.962 kilonewton. Interesting, but for the clearance, which hardness of the material did you choose? That is what I would also want to know, and and why. 0.06 because of the thickness. On what basis do we choose the clearance constant? It is a very interesting question. Um, the basis can be um, the basis can be um, the actual hardness of the material. So generally, for soft materials like aluminum, magnesium, we choose the um, the very less um, constant value. And then for the materials like alloyed aluminum and brass and softer steels, we choose medium level um, um, value. And then for high strength steels and high strength alloys, um, we choose the value which is the highest. Um, but the but these constants have also more values. I just chose three here. You can take a look at the literature. You can take a look at different books. So different researchers and different scientists, because these are empirically calculated values, so they have calculated them differently for different materials, and they serve a different purpose. But yeah, that is the general feedback which I can give you. Of course, there is more information available in literature. There is more information available online, and you can take a look at it there. Super. That's good to know. And yeah, interesting. I see that you are getting along. Okay, so now we have a different clearance, 0.225, and of course it would vary because of the value of clearance constant which everybody is choosing. Um, yeah, but it is okay and good. Now let's go to the next sheet of bending. Um, and what we do here is that there are other calculations for bending, but here we are just doing very simple basic calculations. Um, and what we do here is um, put the values of what we need. So the so let's say that the bending angle of the tool is 70 degrees, and the bending radius is relatively larger. Let's say it is not even 5, 7 millimeters, and the sheet thickness is relatively higher, 5 millimeters. Um, and then what here I have applied a conditional, so the bending factor is automatically chosen based on the values which we give here, and then the achieved angle of the part, let's say it was 70 and then we achieved was 62 degrees. So we see that the bending allowance should be 10.56 millimeters, and the spring back in the sheet is, depending on the achieved part angle here, is around 11%. No, this is not correct. Yeah, so it is basically not in percent. Um, so this is basically 0.11 ratio, which then corresponds to 11%. And now let's take another example of where we are bending it to 90 degrees. The bend radius is quite small, it is 2 millimeters. Sheet thickness is also quite small, it is 2 millimeters. Um, and the bending factor still is 0.33, and the achieved bend angle in the sheet is, let's say it is 80. So then we see that the bending allowance is 4 millimeters only instead of 30 millimeters, which was previously. So this is how you can use this sheet um, for your advantage. So what you can do is you can continue using these sheets. Let me show you an example of drawing process where it is quite a simple calculation. There are very few inputs, but there is a lot which we are getting as an output. So if I say that the blank diameter is 25 millimeters and the punch diameter is 10 millimeters, so the draw ratio is 2.5 millimeters. And then here I have added a comment that the upper limit should be less than 2. So if the draw ratio is 2.5, then it will be difficult to process it using this method, and then there are other methods to do it, which is incremental deep drawing and so on, which we are not going into right now. But what we need to do is we either need to increase the punch diameter or decrease the blank diameter so the draw ratio can stay below 2. So what I will do here is I will write here 15, and the punch diameter is 10. Now the draw ratio is 1.5, which is less than 2, so that is okay. And then what I want to do is I want to write here the thickness of the sheet. Let's say the thickness of the sheet is 4 millimeters, and the tensile strength of the material is 300 MPa. Then the force calculation, the total force required is almost 30 meganewtons, which is quite large. And but this is a very basic calculation, and it yields these results. We will look into these results later on how they correspond with the actual experimental values and how they correspond with the numerical simulation values. But yeah, you can use this sheet for your advantage. Okay. um, Super. Now what I want to do is, these are the basic general sheet forming processes, and now we want to talk a little bit about special processes. Um, so one of the processes is stretch forming, which is a metal forming process that simultaneously stretches and bends a selected material over a machined foam called a die. To form a part with one or several different curved radii, the process produces perfectly curved parts with smooth, wrinkle-free contours. So you can see that we have a die which has a specific shape, And what we do is we hold the sheet with a specific force and then push the die into the sheet, and whatever the shape of the die is, the sheet will form into that shape, and we will get our desired results. And then there is roll forming operation, um, which is basically how a combination of rollers is used. Um, it's a continuous bending process in which opposite rolls are used to produce long sections of formed shapes from coil or strip stocks. Several pairs of rolls are usually required to progressively accomplish the bending of the stock into the desired shape. Um, there is a very interesting video about it. Let me see, where is that roll forming? Yes. So let's watch this video together. Oh, come on. Okay, interesting. And then what I would like to quickly reach is, um, where was I? Yeah, and then I would like to quickly address is metal spinning. It is a method of forming rotationally symmetrical sheet material parts. In spinning, the sheet metal discs are formed into rotational symmetrical hollow shapes. The blank is clamped. So if you will see here, um, the blank is clamped between a clamp and the die. And what is then done is the the die rotates at a very high speed, and then we use a rolling tool to shape the die um, onto the onto to shape the sheet stock sheet metal onto the die, and in the end we achieve our parts. um, I found a short and very interesting video to explain this concept as well, which we can see here. So here you will see that um, sheet metal is held between a clamp and a die, and then we have a forming tool which will be used to shape this sheet or cover it over the die. And then of course you will see that there are different steps involved in shaping it more accurately and more precisely. Here the work is being done manually, but of course it can also be done using a numerically controlled or computer numerically controlled machine with more accuracy and more um, consistency. And then now what they're doing is basically, depending on the part which they needed, they're just cutting into the end of the part. Stopped it, the part is cut, and here we get the desired um, component. So yeah, that's about it. And now we come towards the conclusion. So in today's lecture, we studied what is sheet metal and why its forming is so important. We try to understand the basic attributes and properties of sheet materials, the classification of sheet metal forming. We learned to do simple calculations for different sheet metal forming operations. We used the developed sheet to apply the simple calculations for solving simple iterated problems. And of course, such sheets can be made for relatively bigger and more complicated formulas and these things which you can do depending on your needs and requirements in the future. And then we clarified the concepts of some more complicated sheet metal forming operations using interactive videos. And now we are open for discussion. We still have 5 minutes to go, so if you have any questions, you can ask. Um, and yeah, um, on the other hand, what I would want to do is I would write all the registered students an email about the time of the the two extra lectures which we need to set up, and yeah, just keep checking your email, and whenever you find appropriate, if you will find the time appropriate, just appear for the lecture. It will be interesting. Um, the question is, how do we make use of the bending allowance that's calculated? Um, it depends. So depending on the shape and the bending angle, we get a value of bending allowance, and we want to use that as a difference between the die and the punch. How it is incorporated in the process. Yeah, so it is basically incorporated in the design process of the die and the punch. If we know that we want to bend the sheet to a certain angle, and we know that what is the thickness of the sheet and other factors, then we can calculate the bending allowance and can incorporate that in the design of the die and the punch. So there is allowance between both, where the sheet bending can take place without sheet thinning. I hope that answers your question. Professor, so Mr. Rajiv, does that answer your question? Then I can, okay, yeah, okay, so you've said okay, thank you. Then I can move on to the next question. Professor, please clarify on the Excel worksheet. I shared the sheet with you. We tried to run some examples, put in some values, and get the answers. So basically, that sheet is more like a calculator for the formulas which we studied in the slides. So it acts as a shortcut. You don't have to use a calculator to do all these calculations. You can just quickly use the sheet, plug in all the values, and get the desired results. I think that's what we try to do in the lecture as well. I showed you some examples. I wanted you to solve some examples. And yeah, in any ways, I hope that answers your question. Um, if it doesn't, then please explain it a bit more, and then I will be able to help you more. Um, is the workpiece heated for some deep drawing, or every time cold metal is used? It depends. Um, we will do a case study where we will in the next lecture from my master thesis, where we did certain work and how we did it and why we did it and so on. We will do all that. But um, generally, deep drawing process is a cold operation. But I don't know, for specific cases it can be warm, but of course not hot. Um, but it is a, generally it is a cold operation, because when we are when we are drawing a component, when we are drawing a sheet into the desired shape, we also want um, it to strain harden, so it has a certain stiffness and strength associated to it, um, and that is why we usually cold form it. Most of the components, but of course the operation can be done at different temperatures. I hope it answers your question. Do we have any other questions? Seems like no. Then what I would do is I would want to